Okay, in this video, I'm just going to work an example of a gas law problem. So let me get it written out, and then you guys pause the video, see how you can do, okay? So a gas sample is in a sealed container with a volume of 2.5 liters and a pressure of 1.0 atmospheres at 20.0 degrees Celsius. Okay. Now we're going to heat that vessel up. So if the vessel or container, whatever, is heated to 50.0 degrees Celsius and the volume increases to 3.0 liters, what is the new pressure? Okay, so the gas is in a container, has a volume of 2.5 liters, pressure of 1 atmosphere, and temperature of 20 degrees Celsius. We heat it to 50 degrees Celsius, and the volume increases to 3 liters. Just assume the vessel can change volume, obviously. What's the new pressure? Okay. So let's take a look here, and I'm going to start by writing down the one gas law that we really need, PV, the only gas law we really need, PV equals nRT. Okay, and now I'm going to go through and I'm going to look at this problem. I'm going to find pressure, volume. Let's just start with pressure. Okay, here's our original pressure, and the question asks for the new pressure, so that's pressure. Okay, and then let's just do V since it's next. 2.5 liters and 3 liters, so that's V. Let's see. I'm going to skip N and R for a second and do temperature. There's 20 degrees Celsius and 50 degrees Celsius. That's temperature. Okay, what do you notice here? You notice that pressure changes, volume changes, and temperature changes, but what doesn't change? N and R do not change. These are constant. And because they are constant, what I can do is rearrange PV equals nRT, isolate what's constant, and what's variable, and we can make ourselves a new equation. Okay, so we get PV over T is equal to N over R, which we can set over equal to PV over T, which means our equation that we want is P1 V1 over T1 is equal to P2 V2 over T2. This is sometimes called the combined gas law because we've combined a couple of gas laws. Okay, so let's kind of map out what we're going to do. We need to find pressures, volumes, temperatures for initial and final conditions. Let's just do our initial right here and then our final. So P1 is equal to, let's scroll back up, initial pressure is 1 atmosphere, 1.0 ATMs. Okay. Let's see. V1, 2.5 liters. That's supposed to be liters. And T1, what's T1? Don't tell me 20 degrees Celsius. 293 Kelvin. Remember, temperature in Kelvin is equal to temperature in Celsius plus 273. Okay. And that's given on the exam, by the way, that conversion, the 273. Now, let's find our P2. P2 we don't know. V2, that is right there, that's 3.0 liters. And T1. T1, there it is. 50 degrees Celsius plus 273 gives me 320. Yeah, I just write it out. 50.0 degrees Celsius plus 273 is equal to 323 Kelvin. Okay. Now, we know our variables. We know what we need to find. What I like to do now is I solve the equation before I plug a number in. So I'm solving for P2. The reason I do that is because the letters are just easier to move around. So I'm just going to write everything over again. P1 V1 over T1 is equal to P2 V2 over T2. And now multiply by T2 over V2. So I find that P2 is equal to T2 P1 V1 over V2 T1. Yeah, it does get a little confusing. You gotta remember to plug everything in the right spot, but you can do it. So T2, let's shrink it down a little bit so we can see everything. Our T2 is 323 Kelvin. P1, 1.0 atmospheres. V1, 2.5 liters. V2, 3.0 liters. And T1, 293 Kelvin. Now, does it matter which units I use? Kind of. For everything but temperature, as long as they're the same on both sides of the equation, it's fine. Look, we have liters and liters, okay? So it doesn't really matter. The only thing you gotta do is you gotta make sure everything is in Kelvin. You cannot do a gas law problem if you do not have it in Kelvin. All right, just to double check, liters cancel, Kelvin cancels, we're left with atmospheres here. That's what we're looking for. We're looking for a pressure. So we get 0.92 atms. All right. Be sure you can work that on your own. And more videos coming soon, I guess.